Okay. When we were talking about moment of inertia, I showed you this little demonstration. We have a disc and a hoop. They are pretty close to the same mass. They may not be exact, but they're very, very close. This one's made of wood, this one's metal. They have the same radius. When I put them on a track and start them at the same height from rest, the disc wins. The disc wins every time. Okay? And that's because it has a smaller moment of inertia. Smaller moment of inertia means it's easier to make it rotate. It will have a greater angular acceleration. Okay? So it will always win the race down the hill. Turns out, even if they weren't the same mass or the same size, as long as they were not big enough for drag to be significant, and as long as they didn't slip while they were sliding, as long as they rolled perfectly, the disc will always win. Even if it has more mass, even if its radius is bigger, the disc will always win the race. Okay? The only time that won't be the case is if they slip, so they're not rolling perfectly, or if drag becomes a factor. Okay? To show that to you, it turns out all objects with their mass distributed uniformly, they will always get to the bottom at the same time. So I have here some cups. Nothing terribly exciting about them. They're obviously different sizes. They have different radii. This guy fits inside this guy. They have different masses. But the mass is distributed the same way. They're both cups. They both have lips on the top. They're both cylindrical. Now, because of the lip, they tend to roll off the track. So I'm going to start them a little lower on the track, but I'm going to start them at the same height. And I'm going to start them both from rest. So when I let go, I'm supposed to catch it. When I let go, they both get to the bottom at the same time. They both hit the book at the same time. To make it a little more dramatic, two cups, obviously different masses and different radii, but the mass is distributed the same way. If I put them at the same height, they both hit the book at the same time. So that's something that's really interesting. As long as the mass is distributed uniformly, the same way, the same result happens. Okay, so somehow mass and radius don't matter. And it turns out energy is a really easy way to prove this mathematically. Leave this down. Okay, so we have our incline, we have our hoop or our disc or our cup, whatever you want it to be, at the top. It's released from rest. And it rolls to the bottom. What I'd like to know is the speed of the center of mass. How fast is the center of mass moving? Whichever one has the greatest speed at the bottom won the race. So energy. Number one, we're assuming our objects are not large enough for drag to be a factor. Nor are they going to go fast enough for drag to be a factor. We're also assuming that they're rolling without slipping. They're not sliding while they roll as well. That's an important distinction. If they're slipping and sliding while they roll, there will be work done by the kinetic friction. If they don't slip, and they just roll perfectly down the incline, then it's only static or rolling friction that's acting on them. The rolling friction is what makes them have rotational kinetic energy. So that is swallowed up in the term of having kinetic energy. We don't have to look at the work done by that. So work in this term is only necessary to use if there's kinetic friction. So there's some sort of sliding of your object. So we're going to assume they're rolling without slipping, no sliding. So our work term is 0. So we need to look at the energy initially versus the energy finally. So initially, if we choose this point where the center of mass is to be y equals 0, then y initial, okay, height is from the bottom to the incline. What if I measure from the center to the center? It's going to be the same thing, because this center is a distance of radius r above the bottom. This is a radius r above the incline. So y initial will simply be h. The total vertical distance our object is going to move through is whatever h happens to be. Okay. So that means initially our object has gravitational potential energy of mgh. Finally, our object has no gravitational potential energy because it's getting down to where we defined y to be 0. Initially, the kinetic energy is 0 because it was released from rest. At that instant in time, the velocity and angular velocity are 0. It certainly doesn't stay 0. They accelerate and roll down the hill. But at that instant, it's 0. Finally, it's rotating. So it has rotational kinetic energy. But the rotation axis is not fixed. It physically moved all the way down the incline. So it also has translational kinetic energy. So we simply add them together. Add them. So we're just saying it has this much rotational energy and this much translational kinetic energy. So totally it has the sum of the two. So setting this into our conservation of energy equation, all the energy we start with has to equal all the energy we end with. This equation is valid whether it's the hoop, or a disc, or the cylinder, or a sphere. Doesn't matter. Whatever object's going to roll down the hill, as long as it starts at rest, this equation is perfectly valid. It's when we start plugging values in that it's different for one object versus another. So for example, for the hoop, let's say we're looking at the hoop. So the hoop is up at the top, starting from rest. It has some mass m, some radius r. We could certainly measure both of them very easily. We have mgh, but I, we get I off the table. 1/2 I for a hoop is simply mr squared. Now we're looking for v, the speed of the center of mass. V and omega are related. What's the relationship? What can I plug in for omega so I can write it in terms of v?
D over R.
V over r. And that will be the speed of the center of mass. So these v's are the same. Notice, there's a mass in every term. So mass cancels. In this term right here, since we've made the substitution of V over R, but this term is squared, we have an R squared on the bottom, but we have an R squared in here from the moment of inertia, so the R squareds will cancel. So we have GH is equal to 1/2 V squared for this first term, plus 1/2 V squared for this second term. 1/2 plus 1/2 is 1, so that's equal to V squared. So V is equal to the square root of GH for the hoop.
Is that an R squared on the bottom of the V?
Well, it's V over R, but this whole term is squared.
Oh, okay.
So simply the speed at the bottom, this is specifically the speed of the center of mass. The speed at the bottom is equal to the square root of GH. So it simply depends on how high the incline is. What about this is going to change if we're looking at the solid disk? The I. So we'll still have MGH. We're going to have 1/2, but I for a solid disk is 1/2 mR squared. Omega is still V over R. That quantity is squared. The masses still cancel. The R still cancel. So we get GH is equal to 1/4 V squared plus 1/2 V squared, which is 3/4 V squared. So V is the square root of 4GH over 3. For the hoop, it was 1GH. We have 4/3 GH now. 4/3 is bigger than 1. The speed of the center of mass is larger for the solid disk than it is for the hoop. Masses and radii cancel out. That's why any disk will beat any hoop, as long as drag is insignificant and as long as they don't slip or slide. We could certainly do the same for a solid sphere. Say we had a bowling ball and we wanted to roll it down the hill. I would be different, that's all. I would be different, so we'd end up with a different result. So energy's pretty nifty, actually. As long as you want to relate some sort of height to a speed, energy is a fantastic way to go. It easily relates the two. Okay. Questions? Now you do need to keep in mind that energy cannot be used in a collision, and it cannot be used in a situation where mass is redistributed. For example, an ice skater bringing her arms in. You cannot use energy in that case. Energy, in terms of potential to kinetic, is not conserved. Okay? So if you have a collision or a redistribution of the mass, you have to use momentum. Energy will not work.